Today we'll talk about the derivative rules with the natural functions, and this will be part one. So in this part, let me remind you what the natural functions were. So there are two natural functions. There's e to the x, that's one natural function, and then there's ln of x. And these are inverses of each other, meaning if you have your domain here, and you have your range over there, and you plug in a point, let's say 2, the function e to the x will take 2 over to e squared, and then the function ln of x will take this e squared back to 2. And we memorize things or learn things like e to the ln of the anything is the anything, or ln of e to the anything is the anything. So it goes, you can go either way because they're inverses of each other. One takes you forward, right? So one takes you this way, and the other one will take you back. And we want to learn how to take the derivatives of these things, because if we can take the derivatives of these, then we can take the derivative of any exponential function. So suppose I had like 2 to the x, and I want to find its derivative. Well, if I know how to take derivatives of e's and ln's, then I can simply write 2 to the x as e to the ln of the anything is the anything, so e to the ln of 2 to the x. It's the same thing. The anything is equal to e to the ln of the anything. And then I could write this as e to the x ln of 2. And so if I can take derivatives of e's, then I can take derivatives of 2 to the x. And the same thing works for log base 2 of x. So if I know how to differentiate the ln function, I should be able to differentiate log base 2 of x, because log base 2 of x is equal to ln of x divided by ln of 2. And these are identities we learned on the first exam. And so our goal is to learn how to differentiate today. We're going to learn how to differentiate e to the x. And then on, I think, probably Wednesday, we'll learn how to differentiate ln of x. So we'll do this in two parts. And so let's take a look at the first rule. So our first rule, we'll call this the natural rule part 1. And this tells us how to take the derivative of e to the x. So d dx of e to the x, and this is one of the easiest rules to remember because it's just itself. So the derivative of e to the x is just e to the x. And so if you look on that paper, you'll see the quote, or we can write down the saying, the derivative of e to the x is just e to the x. And I just noticed on that paper that's not written down. So you can add this to the handout I gave you. The derivative of e to the x is just e to the x. And so we want to use these rules. So let's take a look at an example on here. So here's an example. And how are we going to use this? So we want to find the derivative. We want to find the derivative of 3x to the 5th plus 2e to the x minus 5. And the way this works, it's just like, so find f prime of x. It's equal to, and let's write f of x above it. It doesn't hurt to copy these down and kind of say them as we go. So we have 3x to the 5th plus 2 e to the x minus 5. And so to find the derivative, f prime of x is equal to, so the 5 is going to come down, so I get 15. You can take away 1 from the power, x to the 4th, so it's just a power rule, plus 2 times e to the x. So the derivative of a constant times a function is just a constant, times the derivative of the function, and the derivative of e to the x is just e to the x, minus, and finally the derivative of 5, which is 0. And so this is equal to 15 x to the 4th plus 2 e to the x. Let's look at another example, and in these two examples here, A and B, we're going to use both the product rule here, and then the quotient rule, obviously, down here. So let's start with this one. And let's just copy it down. So example 2, part A, we have g of x, example 2. We have g of x equal to x cubed e to the x. Now when I look at this, hopefully you realize you're supposed to use the product rule because there's two parts. Here's the first function, and then next to it is the second function, e to the x. So x cubed times e to the x. And I want to use the product rule. So the product rule says g prime of x will equal the derivative of the first, so 3x squared, times the second, so times e to the x, plus the first, which is at x cubed, times the derivative of the second, which is again is just e to the x, because the derivative of e to the x is e to the x. That's the new rule we just learned. Make sure you can identify each of the little pieces here. So here's the derivative of the first function. So here's my circle prime. And then it's multiplied by the second function. And then I add the first function. So it's just the product rule. So there's the first function. Times the derivative of the second function. So this is, I guess, a square maybe, or prime. So there's the product rule. And the rest is just some algebra. So remember, when I have an expression like this here, I want to factor it. So this is going to be equal to, factor out what they have in common. So they have an x squared in common. Right? There's an x squared and there's an x cubed. So I factor out the lowest power. And they also have an e to the x in common. So I factor out an e to the x. And I play this game. Something goes here, plus, just copy down the plus sign. Something goes here. When you multiply by this, you get this whole expression above back. And so can you figure out what goes here times this equals that? If you think about it, you're going to need a 3. And then you have the x squared, and you have the e to the x, so that's good. Then over here, you have an x cubed, and you have an x squared here, so you're going to need an extra x. So this is going to equal then x squared e to the x all times 3 plus x. And that is my answer. All right, let's take a look at part B now. So on part B, we have y equals e to the x divided by x plus 1. And so this is obviously going to be a quotient rule. So I have a high function and a low function. And remember, it's low d high minus high d low, all over low squared, and away we go. So y prime is going to equal low, so x plus 1, d high, so remember, derivative of e to the x is just e to the x, minus the high function, which again is still e to the x. Then d low, now d low is just 1. Right? Remember, your low function is x plus 1, so derivative of x is 1 plus 0, so I just write down 1 here. All over my low squared, so x plus 1, quantity squared. And so this is equal to, we have, and if you want, we can multiply through by the e to the x. So let's multiply through by the e to the x. So I have e to the x times x, and e to the x times 1. So I'm going to get x e to the x plus e to the x times 1, so e to the x, and then minus an e to the x, all divided by x plus 1, quantity squared. And in this case, these e to the x's will cancel, and I'll be left with my final answer, x e to the x, all divided by x plus 1, quantity squared. So here's my answer for this one. Okay, so what have we done so far? Let's take a look at these slides here. So we used the first 4 rules to differentiate an expression. We used the product and quotient rules to differentiate an expression involving the natural exponential function. And then the last thing we want to do is we want to use the chain rule here. And actually, there's one more thing after this. So we want to use the chain rule to differentiate these following 4 expressions. And some of these expressions use not only the chain rule, but also the product rule or maybe the quotient rule. on top of the new rule we learned today. So let's just start over here with part example 3. Okay, part A. We have f of x equal to e to the 3x. Now, when we use the chain rule, you have to see inside versus outside function. So look at this and try to think, which one is the inside function? All right, so it turns out that 3 to the x is the inside function, whereas e is the outside function. So maybe we should just review just for 1 minute this idea of inside and outside. So if you look here, let's do like x squared plus 1 cubed. And then let's do e to the x squared plus 1. And let's do ln of x squared plus 1. And let's even do sine of x squared plus 1. So when you look at these, hopefully you see inside and outside functions. So of course here, that's the inside. Here, that's the inside. Here, that's the inside. And here, that's the inside. The only one that gets a little bit confusing is e, but it's e to the x squared plus 1. So it's like the e's holding on to that. Right? The cube's holding on to this, the ln's holding on to that, and the sine's holding on to the x squared plus 1 here. Once you identify inside, of course outside's easy. Right, so the 3 is the outside, the e is the outside, the ln is the outside function, the sine is the outside function. So once you make this identification, these problems become pretty simple because you're just using the chain rule. And remember, the chain rule says the derivative of the outside times the derivative of the inside. So let's come back up here and look at this problem. And so now the derivative of the outside, derivative of e, is just e again. So derivative of e to the 3x is just e to the 3x. So that's the derivative of the outside times, now the derivative of the inside, the derivative of 3x, is just the number 3. So then I'd probably write this as 3 times e to the 3x as my final answer. Although you could leave it like this. Now on part B, what do we have? So on part B, we have g of x equal to x squared e to the 5x. And now you have to ask yourself the question, which rule are you going to apply first? Now you know you're taking a product here because it's x squared times e to the 5x. And there's also going to be a chain rule because you have this e to the 5x. So which rule are you going to use first? If you say the chain rule, you're going to be wrong because the chain rule will only involve this e and the 5x. It does not involve the x squared. So you have to apply the rule that applies to everything. And that would be the product rule. Because if you think about it, the product rule, here's my first function. So x squared is my first function, whereas e to the 5x is my second function. And so now I simply take the derivative by using the product rule. So g prime of x will equal the derivative of the first, which is a 2x, times the second, which is just e to the 5x, you just copy it down, plus the first, so nice and easy, copy it down, times the derivative of the second. Now for the second function, remember it's a chain rule, and here's your inside function, and your e is your outside function. So it's the derivative of the outside, which is just e again, so e to the 5x, derivative of e is just itself, times the derivative of the inside, and the derivative of 5x is just the number 5. And so this is equal to, let's factor out what they have in common. So there's an x and an x squared, so I'll factor out an x. Number-wise, I should have done that first. Number-wise, they don't have anything in common. A 2 and a 5, they're both prime. They don't have anything in common. And then they certainly have an e to the 5x in common, so I'll factor that out too. And I play this game. What goes here plus what goes there. When you multiply this by that, you get this back. All right, so obviously you need a 2, and that's it. 2 times x e to the 5x gives you 2x e to the 5x. I mean, just say it. 2 times this, 2 times x e to the 5x is 2 times x e to the 5x. They're exactly the same thing, right? Just say it, and you can get yourself to believe it. Over here, I need a 5. because there's not a 5 over here. And I'm also going to need an x because this is x squared. Now I have one x there, so I'm going to also need an x. And so that's my final answer. Maybe I'll just kind of clean it up so you can see it real clearly here. So it's x e to the 5x all times 2 plus 5x. All right, part C now. So that was a product rule with a chain rule inside it. Part C is h of x equal to e all raised to the x over x plus 1. All right, so when I see this, I know I'm going to have to use a quotient rule at some time because there's a quotient right here. And then I'm also going to use a chain rule because there's an inside function and an outside function. But which rule do you apply first? If you say the quotient rule, you're wrong, because the quotient rule only involves this inside piece. Whereas if you say the chain rule, you'd be right, because when you identify these things, here's my inside versus here's my outside, it'll involve everything. And so let's take the derivative of this using the chain rule. And so I have h prime of x is equal to the derivative of the outside. So derivative of e is just e again, so I just copy it down, e to the x divided by x plus 1. Then times the derivative of the inside, and now this is where you use the quotient rule. So you have low d high, so low is x plus 1. D high, derivative of x is just 1, minus the high function, times derivative of the low function. Now derivative of x plus 1 is just times 1, all over low squared, so x plus 1 quantity squared. If you simplify this on top, you have x plus 1 minus an x, so x's are going to cancel, and so I'm going to get over here e to the x divided by x plus 1. I'll put parentheses around, just kind of put it off there. And then on top I'll have a 1, and then this will be divided by x plus 1 quantity squared. And so if you like, I guess I could write this as e to the x over x plus 1. You can choose to put parentheses on the top or not. It really doesn't matter. It's clearly all on the top. Then all divided by x plus 1 quantity squared. That's probably how I write it. So that one was a chain rule with a quotient rule inside it. So notice this. Over here, B is a product rule with a quotient rule inside it, and also a power rule, really. And then H is a chain rule with a quotient rule inside it. Did I say that right? Let's go back up here and make sure I said that right. So part B is a product rule with a chain rule inside it, and also a power rule. Whereas in part C, this is a chain rule with a quotient rule inside it. And then in part D, finally, let's take a look at this one. Part D, I have y equal to e to the x squared plus 1 to the 10th power. And I'd like for you to think just a second about what rule, or actually rules, there's two of them in some sense, and more, but what two big rules are we going to use here? Just like over here, this was a product with a chain inside it. This was a chain with a quotient inside it. This one here that we're doing right now, this is a chain rule with another chain rule inside of it. It's a chain. I mean, that's why they call it a chain rule, really, because chains sort of link together in some sense. So when I take the derivative of this, the first thing I do, let's identify inside and outside. So here's my inside function, and then here's my outside function. And so I know that y prime is equal to the derivative of the outside. So derivative of e is just d again, so e. And then I have x squared plus 1, all to the 10th, times the derivative of the inside. Now when I take the derivative of the inside function, notice it has an inside and an outside. So its inside is this x squared plus 1, whereas its outside is to the 10th power. So that's why it's a chain. You can see I have a green circle, 2 green circles, and then 2 red circles. And so now, if I want to take a derivative of x squared plus 1 to the 10th, the 10 comes down. So it's the derivative of the inside, right? The 10 comes down, x squared plus 1 to the 9th power, times the derivative of its inside, which is 2x. The derivative of its inside, derivative of x squared plus 1, is just 2x. And so this is equal to, I have 10 times 2, so that's 20. And then I have 1x, there's an x there, times an x squared plus 1, all to the 9th power. And then times this e raised to the x squared plus 1 to the 10th.
Finally, we want to apply this
to exponential functions in general. So what do I mean by that? Right now, we know how to take the derivative of e to the x, basically. So derivative of e to the x is e to the x. I mean, we also know how to take derivatives of constants. Remember, derivative of constant is 0. We know how to take derivatives of x to the n, so we can do power functions and constants. So that's n, x to the n minus 1. Now we can take derivatives of exponential functions, the natural exponential function. But we want to be able to do exponential functions in general. So how would I do like something like 5 to the x? And to do 5 to the x, the idea is you can write this in terms of the natural exponential by remembering that identity, e to the ln of the anything is the anything. So 5 to the x is the same as e to the ln of 5 to the x. Because these are inverses of each other. So if you think about the picture here, here's 5 to the x. Here's e to the x. Okay, so e to the x is going to take 5 to the x over here. And then it's going to ln is going to take it back. Actually, the picture goes the other way. So here, let me switch colors so I can show you. We're actually going the opposite way. So let's go this way. So 5 to the x, ln of x takes it this way. It doesn't matter which way it goes. So if you plug the ln function, it's going to take it over here to ln of 5 to the x. And then if you take the e function and apply it to that, it's going to take it back to 5 to the x. All right, so you plug this thing in for here, and it's going to take you back to 5 to the x, because they're inverses. So if you go this way and back, you wind up where you started, or if you go this way and back, you wind up where you started. And if you see this, what we can do is, remember, this little exponent can come down in front, and so I get this to be e to the x ln of 5, and I can take the derivative of this thing. All right, so let's do this right below it. So think about this. If I have 5 to the x, which we just said was equal to e to the x ln of 5, how do we take a derivative of this? Well, there's an inside and an outside. So let's circle the inside. So here's my inside function, which is just some number ln of 5 times x. And then I have an outside function, which is just my e function right here. And then I know by the chain rule, it says it's the derivative of the outside, so the derivative of e the function is just e again. So I have e x ln of 5 times the derivative of the inside, so the derivative of x ln of 5, well, it's just x times a number. So x times a number, the derivative is just the number ln of 5. And if we rewrite this, with understanding that this thing here, or this thing here, is the same as this thing here, right? So it must be the same as that thing there. So this is just equal to 5 to the x ln. Let's erase this so I don't confuse you guys here with what this is, ln of 5. And so the moral of this story is I do not need to know how to take the derivative of this thing, right? I don't need to know how to take the derivative because I know how to take the derivative of this thing, and I can convert these right into those. And if I can do that, I can take its derivative. Now, sometimes, if you do this enough, we will memorize a rule. So if you would like to have another rule, I can give you another rule. So if you would like a rule for how do you take the derivative of a to the x, well, it's just what? Well, it's just going to be a to the x ln of a. I mean, think about it. We got it right there. So if you look at this thing, we saw that the derivative of 5 to the x was just 5 to the x ln of 5. So if we follow that pattern, a to the x, the derivative would just be a to the x ln of a. We're not going to memorize this rule because I expect you, or you're expected, to be able to do the same thing I did here when you have to take the derivative of a exponential function in general. So let's do some examples of this. All right, so let's take a look at these two examples right here. All right. So in part A, what do we have? And this is example 4. Right, working with exponential functions in general. So we have g of x is equal to x squared 3 to the x. So now before can take this derivative, I need to write all the exponentials in terms of e's. And that's not too hard. So it's just equal to x squared. And e to the ln of the anything's the anything. So it's e to the ln of 3 to the x. And so that's equal to x squared e to the x ln of 3. Now, a lot of times students will stop right here thinking they're done, but have you taken the derivative? Nope. All you have done is rewrote x squared times 3 to the x in a form that you can now take the derivative of, because you apply your natural function rule for the exponential function, for the natural exponential function, to this thing. All right, so g prime of x, what is it going to be? Well, first decide which rule are you going to use. So if you think about it, which rule applies to everything, and hopefully what you see is that it's going to be a product rule, because you have the first function, which is right here, times the second function, which is right there. And so I apply the product rule to it, which says g prime of x is equal to the derivative of the first, which is 2x, times the second, so I just copy down e to the x ln of 3, plus the first function, which is x squared, times the derivative of the second function. So remember the second function, this is going to be a chain rule, because you have an inside and an outside. So derivative outside is just e, derivative e, which is e, and x to the ln of 3 times the derivative of the inside. Now derivative of the inside, this is just a number times x, so it's just a number, so times ln of 3. And so this will be equal to, and now the rule is, and so notice, since I wrote this as this 3 to the x, really as e to the x ln of 3, notice that this is still 3 to the x, and this is still 3 to the x. So I'm going to write this back in the form that it was given in. So I have 2x times 3 to the x plus x squared times 3 to the x ln of 3. I'll factor out what they have in common. So they have an x in common and a 3 to the x in common. And so it's all times something plus all times something there. So what goes here times this gives me that, and that's just the number 2. And then what times here times that gives me this. And so I'm going to need an extra x, and it looks like an ln of 3. And so this is equal to x, 3 to the x, all times 2 plus x ln of 3. So that's the first one. The next one, part B, I have h of x equal to 2 times 7, all raised to the x squared plus 1 quantity squared. Right, just the 7's raised to that. And if I want to take a derivative of this, again, I need to write this thing, I need to write this thing right here in terms of e's. And so I just use that simple identity, e to the ln of the anything's anything. So I have 2 times e to the ln of 7 x squared plus 1 quantity squared, which is equal to 2 times e, the exponent can come down in front, so x squared plus 1 quantity squared ln of 7. And so now I'm going to take the derivative of this. And now when you see this, you have to be a little bit careful. So think about what we have here. What we have is a constant, 2, times a function. which is really 7 to the x squared plus 1 quantity squared, but we wrote in terms of e's. So you have a constant times a function. How do you take its derivative? So h prime of x would equal the constant times the derivative of the function. So the derivative of e, you have derivative outside times derivative of inside. So the derivative of e is just e again. So I have e to the, copy it down, x squared plus 1 quantity squared ln of 7, all times the derivative of the inside. So now derivative of the inside, what do you have? You have a constant times a function. So it's just the constant ln of 7 times derivative of the function. So all times 2 x squared plus 1 to the 1 power. Then times the derivative of its inside, which is 2x. So one thing that's not nice about the derivative is you can't really check your work. But there are some things you can check. For example, if you want to see if you took the derivative of something, like did I take the derivative of x squared plus 1? Right, what I can do, right, did I take the derivative of this, x squared plus 1? What I can do is look for the derivative of x squared plus 1 in my derivative, and there it is. There's the 2x. Or did I take the derivative of this square thing? Right, here's the derivative of the square thing right here. So squared 2 times x squared plus 1 to the 1 power. Did I take the derivative of e? Well, here's the derivative of e right there, e, and so on. So sometimes you can kind of point to things to make sure you took their derivatives correctly. So what is this equal to? So let me show you what this is equal to. So this is equal to, and so I have 2 times 2 times another 2, so I'm going to get 8. I have, what else? Let's see, I have an x right here. So keep looking. I have an x right here. So I'll put an x right there. So there's an x. I also have, what else? I have an x squared plus 1 right here. So I'll put an x squared plus 1. And then I also have this e to the, so I have e to the, and let's, for that one, let me remind you, I have this. So let me remind you, before I write this down, what that's actually equal to, because we don't really need to copy down that whole expression, because remember what I highlighted it in green up here is the same as this thing right here. So that's just 7 to the x. So I'm just going to write 7 to the x for that. And then we're left with the last thing to write down, this ln of 7. And we're all done. Oh, I just noticed a little mistake here. When I plugged in for this 7x, it should be 7 x squared plus 1 quantity squared, not 7 to the x. So just notice up here these two things that were highlighted in green. That's equal to that, not 7 to the x, right? 7 to the x squared plus 1 quantity squared. So this is my final answer.